You know, electric motors are pretty much the invisible workhorses of our entire world. They're in everything from our cars to these massive industrial machines. But inside every single one of them, a silent threat is always lurking, a kind of hidden fever that can lead to a total catastrophic failure. So today, we're going to look at how AI can act as a super early warning system for that secret fever. Okay, let's just dive right into the numbers here because they tell a really clear story. When you look at why motors fail, a whopping 78% of all the problems come from just two things, the bearings and the stator. And what's the common enemy for both of them? Yep, excessive heat. That's the main culprit that leads to these really expensive breakdowns. So, that brings us to the big central problem, right? I mean, it's not like you can just stick a thermometer inside a motor while it's spinning at thousands of RPM. No way. The most critical parts are totally inaccessible. So how in the world can we possibly know the internal temperature to stop these failures before they even happen? Well, the answer, it turns out, is hiding in plain sight. It's in the data the motor is already putting out. And researchers came up with this brilliant idea. Let's create a virtual thermometer. So instead of needing a physical sensor, they use artificial intelligence to figure out the internal temperature just by looking at other signals we can easily measure. The tech that makes this all possible is called supervised machine learning. Now, think of it like this. You basically show a computer thousands and thousands of examples. You give it the motor signals, like its speed and the electrical current, and then you tell it, okay, for these signals, this was the exact internal temperature. Over time, the AI starts to learn all the subtle patterns, so eventually, it can look at brand new signals and predict the temperature all by itself. Pretty cool, right? Now, to figure out the absolute best way to do this, researchers set up a kind of competition. They took 3 different AI models and pitted them against each other in a head-to-head challenge. It's basically a tech bake-off to see which algorithm can build the most accurate virtual thermometer. So in one corner, we have the linear model. This is our baseline, the simplest approach you could take. It basically assumes a direct, straight-line relationship. As the signals go up, the temperature goes up. Simple. But in the other corner, we've got 2 types of neural networks, an MLP and a CNN. These are way more sophisticated. They act like this whole team of virtual neurons that can spot really complex nonlinear patterns that the simple linear model would just completely miss. So what's really fascinating here is how the researchers actually proved which model was the best. They didn't just guess or eyeball it, they designed this super rigorous experiment to really put these AI contenders through their paces. They basically ran a 4-step gauntlet. First, they collected a massive amount of data. We're talking 150 hours of a motor running under all sorts of different conditions, from slow and steady to really fast and dynamic. Next, they cherry-picked the most important signals, the motor's speed, its current, and the temperature on its outer shell. Then, and this is crucial, they prepped all that data, cleaning it up so the AI could learn effectively. And finally, it was game time. They trained each model and then unleashed them on brand new data to see how accurate they really were. So, after all that rigorous testing, it's time for the big reveal. Which AI contender actually came out on top? Let's take a look at the results. To judge this whole competition, they used a score called mean squared error, or MSE. It's a way to measure, on average, how far off the AI's predictions were from the real actual temperatures. And with MSE, the rules are really simple. The lower the score, the better the model. All right, first up to the plate, the linear model. It scored a 1.94, which is okay. It's a solid, if not spectacular, result. The researchers themselves called it satisfactory, with most of the errors falling within an acceptable 5-degree range. So this sets our benchmark. This is the score to beat. So how about the first of our neural networks? The Multilayer Perceptron, or MLP. And wow, just wow, what a difference. The MLP scored a 0.31. I mean, that is a massive leap forward in accuracy. The researchers said its performance was much better than the linear model, and it proved it could handle all those subtle shifts between slow and fast motor speeds way more effectively. And finally, our third contender, the Convolutional Neural Network, or CNN. Its score came in at 0.54. Now that's very impressive, and way better than the simple linear model. But surprisingly, it was actually marginally worse than the MLP. And this suggests that, for this specific problem, the MLP just hit the perfect sweet spot. It was complex enough to find those hidden patterns, but not so complex that it started getting confused. So, the crucial point here, when you put them all side by side, the results are just undeniable. I mean, this just brilliantly illustrates the clear winner of this contest. With the lowest error score by a huge margin, the Multilayer Perceptron is our champion, our best-in-class virtual thermometer. But look, this is so much more than just a cool academic exercise. Being able to have an ultra-accurate virtual thermometer inside every electric motor, well, that has some profound real-world implications. This really changes the whole game for reliability. What this all means is that we can create truly smart motors that actually prevent their own failures by telling us when to schedule maintenance. We can boost their efficiency by optimizing how they run in real time. We can seriously increase safety, especially in critical systems like electric vehicles, by avoiding those dangerous breakdowns. Ultimately, this tech helps pave the way for a more sustainable future, one built on incredibly reliable electric powertrains. And that just leaves us with this one fascinating thought. We've just seen how AI can detect a motor's invisible fever. It just makes you wonder, what other critical, unseen failures in all kinds of different systems could we learn to predict next?